For decades, those problems remained locked away, forever out of reach. But deep inside a lab nestled in Santa Barbara, Google is making a bold, almost audacious bet that they've found the key. They are building a quantum computer, a machine designed not just to be faster than anything we've seen, but to tap into the very fabric of reality to solve problems that are, right now, completely and utterly impossible for classical computers. This isn't just another tech upgrade. This is potentially the next seismic shift in technology. It's the kind of leap that reshapes industries, unlocks new scientific frontiers, and fundamentally changes what we believe is possible. Yet, unlike the relatively unified excitement around, say, the early internet or the recent AI boom, the world of quantum computing is a hotbed of debate. Timelines, approaches, even the certainty of its impact. It feels like nobody can quite agree. It's a strange moment, almost like witnessing a company CEO stand on stage, unveil something revolutionary, and then invite everyone in the room to explain why he might be wrong. But Google isn't flinching. They are, as they say, all in. Why? Because they believe quantum computing could be the secret weapon in the most important technological race of our time, the race for artificial intelligence. Imagine AI systems supercharged by the ability to process information in ways we can only dream of today. If they succeed, Google could solidify its position at the forefront of the future. But if they fail, well, it wouldn't be the first time Google lost its lead in a race it helped ignite. One of the most intense arguments simmering in the quantum world right now isn't about if it will happen, but when. Specifically, when will this mind-bending technology transition from theoretical physics experiments and early demonstrations into practical, real-world applications that genuinely make a difference? Google recently stepped into this fierce debate with a new forecast, a countdown that will undoubtedly electrify the quantum enthusiasts and raise eyebrows among the skeptics. Their internal projection? They believe we are about 5 years out from a real breakout kind of practical application that you could only solve on a quantum computer. Now, hold on to that thought because this is a controversial statement. It stands in stark contrast to the wildly divergent timelines voiced by many other heavy hitters in the field. Take the godfather of computing himself, NVIDIA CEO Jensen Huang. When asked about the timeline for significant quantum impact, his view was far more conservative. If you picked 20, he suggested, referring to perhaps 20 years, I think a whole bunch of us would believe it. He echoed the general sentiment of many, stating that most people still think that's like a decade plus out. So, which is it? Are we on the cusp of quantum computers solving impossible problems within the next 5 years? Or is this another instance of technological hype stretching reality into the distant future? Are we looking at a tech shift that's fundamentally overhyped? Or are we simply too early in its development, struggling to imagine its true potential? These same questions, this same mix of excitement and skepticism, have echoed throughout history whenever truly disruptive technologies emerged. Think back to artificial intelligence companies just a few years before 2022. Many saw the promise, but few outside the inner circle anticipated the sudden, explosive impact of large language models like ChatGPT. Or step back even further, to the dawn of computing itself. When computers were first starting to get serious, moving beyond theoretical curiosities and into practical, albeit massive and clunky, machines, their applications were primarily scientific. They were used to calculate ballistic trajectories, break codes, and solve complex mathematical equations for research. That initial, narrow focus was the primary incentive for developing the technology further. But here's the crucial part. As the technology continued to advance, becoming smaller, faster, and more powerful, many applications were discovered that hadn't even been conceived by those early pioneers. Who could have predicted personal computing, the internet, or smartphones based on the room-sized mainframes of the 1950s? The history of technology teaches us that initial applications are often just the tip of the iceberg. Quantum computing, with its unique capabilities, has the potential to follow this pattern. It could unlock entirely new markets, solve previously unsolvable problems in fields like medicine, materials, science, and finance, and deliver massive returns for the early movers who figure out how to harness its power. Where it's truly going to go in the long run? Honestly, I think we are hampered by our limited imaginations to even guess. We tend to project current needs onto future tools, missing the truly transformative possibilities. Google's big moment, the one that truly put the quantum world on notice and shifted the conversation, came with the announcement of their Willow chip in late 2024. This wasn't just another incremental step. It was a breakthrough moment that provided tangible proof of quantum's unique power. Willow solved a specific benchmark problem, not just faster than a classical computer could, but in a way that highlights the fundamental difference in computational capability. How different? Well, Willow took about 5 minutes to handle this benchmark problem. On one of the world's fastest supercomputers, the best classical machine we have, that same problem would take an estimated 10 septillion years. Let that number sink in. 10 septillion. You hear septillion, and your brain nods along. But what does that number even look like? It's a 1 followed by 25 zeros. To wait that long would be, well, literally longer than the age of the universe itself, which is about 13.8 billion years. Imagine a computer running non-stop since the Big Bang, and still not even close to finishing the calculation. This wasn't just about speed. It was a demonstration of solving a problem that was, until that moment, simply impossible within any reasonable time frame on any classical computer, no matter how powerful. It was a clear demonstration of what's sometimes called quantum advantage, or beyond classical computation, though the exact definitions are still debated. But Google went a crucial step further than just a theoretical capability demonstration. With Willow, they also showed a real-world problem that a quantum chip could actually solve, or at least a simplified model of one. This proof point, not just a promise, started to give the technology tangible weight. It showed that the abstract power of quantum mechanics could be harnessed to perform useful computations. The other breakthrough from Willow, arguably even more critical for the long-term future of quantum computing, was a dramatic reduction in error rates. Here's the challenge. Quantum computers are incredibly delicate. The qubits that perform the calculations are highly sensitive to their environment, and they make lots of mistakes. With the best technology currently available under typical conditions, every time you perform about 1,000 elementary steps in a quantum computation, there's likely an error. These errors accumulate rapidly, quickly turning a complex calculation into meaningless noise. We'd like to be able to run computations with many more steps than that to solve meaningful problems. Google's breakthrough with Willow showed that there is a reliable way to reduce those errors, paving a path toward scaling. By adding more quantum bits, or qubits, and leveraging principles like error correction codes, even demonstrating performance below threshold for error correction, a key technical milestone, they showed a way to build more robust, reliable quantum computers in the future. And that, according to the experts, is a critical step toward getting to those real-world applications, the ones that could potentially solve diseases by simulating complex molecular interactions, create entirely new materials with exotic and useful properties we can only dream of today, or answer fundamental questions about the universe by simulating quantum systems. As one expert put it, Willow represents kind of a milestone for the field. We've been wanting to see that for quite a while, and so it's a significant development. But even with these breakthroughs, the scale of the challenge remains immense. The complex problems we hope to solve, simulating molecules for drug discovery, understanding catalysts for efficient energy production, designing advanced materials, might require computations involving billions or even trillions of reliable operations. We still have an enormous chasm to cross between what's possible today and what's needed for widespread practical impact. To get a real feel for this cutting-edge research, we recently visited Google's Quantum Lab in Santa Barbara. It's an incredible place, a carefully controlled environment where engineers and physicists work at the absolute edge of human knowledge and engineering. And I had the unique opportunity, as the first reporter I was told, to actually hold the Willow chip. It's kind of crazy to hold it in your hand. This tiny piece of silicon, maybe an inch or two across, contains the components that performed calculations vastly beyond the capability of the world's most powerful supercomputers. To think about that potential, held right there, is mind-bending. It's so crazy. And we didn't just see the chip. We got up close and personal with one of the most crucial pieces of hardware in the lab, Google's dilution fridge. This isn't your kitchen appliance. It's a marvel of cryogenic engineering, creating one of the coldest places in the universe. Just fractions of a degree above absolute zero, 459.67 degrees Fahrenheit, or minus 273.15 degrees Celsius. Looking inside a dilution refrigerator is like peering into an alien landscape. You see all the different wires, painstakingly routed, connecting different temperature stages that get colder and colder as they descend. At the very bottom sits the quantum chip, kept in this extreme cold to minimize thermal noise that would instantly disrupt the fragile quantum states of the qubits. All of this intricate plumbing and wiring exists because you have a control system running at comfortable room temperature in racks nearby. And you need to make stable, reliable connections all the way down to the chip at near absolute zero for inputs and outputs. It's a breathtaking piece of engineering required just to make the qubit stable enough to work with. The promise of Willow wasn't lost on investors. When the announcement hit in late 2024, it sent shares of Google soaring. Alphabet had its best day since April, a clear signal that the market recognized the potential significance of a major breakthrough in quantum computing. And it didn't stop there. The news created billions of dollars in value for smaller, less proven quantum stocks as well. Analysts noted how this single event focused significant attention on the quantum computing sector. We've seen those names really soaring in the past week. One observed, adding that, "I think people were just reaching for anything with the name quantum in it. Quantum this, quantum that." Google had undeniably kicked off a wave of quantum hype with its Willow breakthrough. And as often happens in the competitive world of big tech, other mega-cap rivals quickly followed with their own quantum announcements, eager not to be left behind. But here's where the market's reaction offers a crucial insight. While the announcements made noise, the market and investors were less willing to buy into the hype generated by Google's competitors, at least based on their initial reveals. This suggests that Google had something here, a demonstrated capability, a proof point that others didn't yet. Let's dig into what the competition announced and why it was perceived differently. Microsoft, for example, announced what it called a quantum computer breakthrough with its new Majorana 1 chip. Amazon also jumped into the quantum computing race, revealing its first quantum chip as just the latest tech giant to make a big play in this space. These announcements bring into focus the different layers of quantum hype we discussed earlier. There's the macro hype, the big, bold idea that quantum computing will someday revolutionize everything from drug discovery and financial modeling to climate prediction. And then there's the company-level hype, where big tech players stake their claim, announce projects, and signal their intent to compete in the race. But, as the market reaction suggested, not all announcements are created equal. Google, Microsoft, and Amazon's updates did make noise. They generated headlines. But unlike Google's Willow news, they didn't move the market significantly for the companies themselves. Why? Because experts saw them as more roadmaps than proof. Microsoft's splashy announcement around their Majorana chip in particular quickly faced serious scrutiny from experts in the scientific community. The core of Microsoft's approach for years has been based on a theoretical concept involving creating a new state of matter called Majorana modes, which could form the basis of incredibly robust qubits known as topological qubits. The theory behind it is beautiful and elegant, offering a potential path to quantum computers that are inherently more resistant to errors. As one expert explained, the theory is convincing that if you can build a device with certain specifications, it will give you a very good qubit. However, realizing this beautiful theory in practice has proven incredibly challenging. So far, it's been very challenging because the devices that they built are a little too dirty. The expert noted, they need to be cleaner. They need to be more nearly perfect than they've been able to demonstrate so far. Essentially, Microsoft is making a long-term, high-risk bet on a beautiful theoretical concept, but one that has yet to be definitively proven in a way that yields a functioning, reliable qubit. Adding to the skepticism is a troubled history. Microsoft had previously claimed in 2018 to have made what are called Majorana 0 modes, a basic building block for their approach, but that claim later had to be retracted after further analysis and inability to replicate the results. This background means the scientific community is understandably cautious. So far, we haven't seen very convincing evidence of the performance of the qubits in the Majorana 1 device. An expert stated, emphasizing the need for verifiable data. We really would like to see a published article that is available to the scientific community so we can see the evidence. And so far, that article hasn't appeared. For now, many are taking a wait-and-see approach with Microsoft's latest announcement. As one person advised, I say just wait and see. I say that Microsoft ought to be given, a few more months to publish the data to have it peer-reviewed. And one way or the other, we're going to find out. It highlights the crucial difference between announcing an intention or a theoretical concept and providing empirical, peer-reviewed evidence of a working technology. Amazon's approach also has its nuances, and experts say it's also in the very early stages. However, it's seen as potentially a viable alternative to Google's approach in the long run. Amazon also demonstrated a step forward in error correction, showing that as they increased the size of a quantum code, they achieved slightly better performance. Of course, that's just, the first step along what is likely to be a long road, an expert commented. But it's an alternative to the Google approach, which might be beneficial in the long run. This pursuit of alternative paths is seen as fundamentally important for the field as a whole. Right now, we really don't know what's going to be the best way in the long run to make a large-scale quantum computer work well. Different companies exploring different fundamental physics approaches increases the overall probability that someone will find a path to scalability and practical utility. However, the current consensus among many experts is that Google, along with IBM, who are working on broadly similar approaches, often called superconducting qubits, are currently far ahead in the race in terms of demonstrated capabilities and progress towards scaling. But staying ahead is the real challenge. And if history is any guide, particularly Google's own history, they know how quickly momentum can shift and how a technical lead doesn't automatically translate into market dominance. For AI, everything changed with ChatGPT. For years, Google researchers had been doing groundbreaking work, publishing foundational papers. But it was OpenAI that finally turned the belief in AI's potential into widespread adoption and tangible revenue. OpenAI reaped the credit, and the users, becoming the public face of the AI boom. Yet, it was actually Google that had quietly laid the groundwork years earlier. Back in 2017, Google researchers published the now famous paper, Attention is All You Need. This academic paper introduced the transformer architecture, the fundamental technological innovation that powers ChatGPT and nearly every large language model dominating the AI landscape today. As one person put it, given that they did come up with AI now, they may not have commercialized it, but they were there ahead of everybody else. Google had that foundational moment, that crucial scientific breakthrough. But it went largely unnoticed by the public until OpenAI, a competitor, effectively deployed it with a product that was simple, accessible, and instantly useful to millions. Now, Google's Willow chip breakthrough may represent a second chance, an opportunity to lead the next big era of technology from the front. It's a shot to turn deep, fundamental research into a defining commercial moment, much like the transistor or the internet before it. Some might wonder, does this quantum push even matter in the context of Google's current challenges, like the intense competition in AI with models like Gemini? So what? Someone might ask. We're going to just decide that all the problems with Google and Gemini and not knowing where they are in the real world should be trumped by this quantum computing? It's a valid question about priorities and resources. But there's a powerful argument that the two fields aren't separate battles but potentially intertwined. Some believe quantum computing could fundamentally supercharge AI itself, boosting Google's position not just in quantum, but in that primary AI race as well. When it comes to AI, many experts think it's likely that future AI systems will continue to make heavy use of conventional computing, but we'll see more hybrid systems with a quantum processor incorporated into the system. What might this look like? One avenue could involve using quantum computers for certain types of data storage or processing that are intractable classically. In principle, you can store a vast amount of classical data very compactly in a quantum computer, leveraging the superposition and entanglement of qubits, However, there's a catch. That process tends to be very slow. As one expert cautioned, if we try to apply a quantum computer directly to problems that involve massive amounts of data, like we do with conventional AI training today, the slow loading and unloading of information from the quantum computer may nullify any advantage in the speed of computation. So, simply swapping out a classical processor for a quantum one for current AI tasks might not work. But there's another, perhaps more promising, potential breakthrough at the intersection of quantum and AI: the creation of data itself. AI's breathtaking progress over the last few years has been fueled by vast amounts of data, largely scraped from the internet. However, models are growing, their appetite for data is increasing even faster, and we are rapidly approaching a data wall. We've simply used up most of the easily accessible, high-quality data available. As models grow, they need not just more data, but different data, novel insights to continue advancing. This is where quantum computing could potentially come in. By their very nature, quantum computers are designed to simulate quantum mechanics, the fundamental rules governing the universe at its smallest scales. Complex physical systems, like molecules, materials, or chemical reactions, are inherently quantum mechanical, and simulating them accurately on a classical computer becomes exponentially harder as they increase in size. Quantum computers, however, are built to handle this complexity naturally. This means they could generate entirely new, synthetic datasets based on fundamental physical principles that classical computers simply can't produce. These unique datasets could potentially provide the fresh, high-quality training data that advanced AI models need to break through the current data wall and unlock new breakthroughs. As Julian Kelly, who works at Google's Quantum Unit, explained, "One of the potential applications that you can think of for a quantum computer is generating new and novel data," he added. "I think quantum computers will provide a lot of training data, which can then be used to solve quantum problems by conventional AI, much better than we've been able to do in the past." It's important to note, however, that not all experts are sold on this immediate synergy between quantum computing and AI. The field is still so nascent, and the specific algorithms for generating useful data or accelerating AI tasks are still being developed. From my perspective as a scientist who works on this, one expert stated candidly, "I think that the claims of quantum computing revolutionizing AI based on what we currently know, I'd say, are at least 90% hot air." And even Google itself, while exploring these possibilities, acknowledges the speculative nature. Julian Kelly admitted, "There may be new methods that only kind of quantum information processing might be able to use to break down some of the fundamental mental barriers that may exist. But that's a little bit speculative, to be honest." Still, Google's strategic focus isn't just on abstract theoretical problems. They are keenly focused on reaching those real-world applications. As Julian Kelly reiterated, "Our focus really has been keeping our eye on when do we actually get to applications that can be solved on a quantum computer better than a supercomputer? This concrete comparison to the best classical machines is their benchmark for progress. So what you see in our scientific results is we're typically making that comparison," he said. "And we think that the most important thing is to do that first, and then have the product side can be involved, once we have like the core demonstration of the technology." This seems to be Google's playbook. Push the scientific results to demonstrate undeniable capability that surpasses classical limits, then leverage that core demonstration to build products and find market applications. It's a strategy rooted in their history, aiming to ensure that this time, the foundational breakthrough translates into market leadership. Google's got its eye on scientific results and product, recognizing that bringing the technology to market is key to turning a breakthrough into a business, and critical if they are to win not just the quantum race, but the next big platform shift. Science is just the beginning. Bringing it to market, creating useful tools that people and businesses can actually use, that's the real victory. For this piece, as you saw, we went right to the source, visiting Google's Santa Barbara Quantum Lab, and we had the chance to sit down with Julian Kelly for an extended interview. Julian has been at Google's Quantum Unit for over a decade, deep in the trenches of this challenging work. He helped us sort through some of the hype and get a clearer picture of the reality on the ground. Here's more of our conversation, weaving his insights into the narrative. Julian, what do you think initially interested a company like Google about this incredibly complex and uncertain space? I think what gets people so excited about quantum computing, Julian explained, is that there are like fundamental theoretical foundations that show that quantum computers can solve problems that nothing else can solve. He emphasized that this isn't just hopeful speculation. It's backed by rigorous physics and mathematics. And I think it's that vision and that rigor, he continued. It gives companies like Google the confidence to make long-term bets in these technologies because we have a lot more certainty than a lot of other emerging technologies that when we make it, it's going to be useful, right? This fundamental guarantee of potential utility provides a strong motivation for the significant investment required. It feels like now, all the megacaps are doing quantum in some form or another. Microsoft, Amazon, IBM, even smaller players. But is it fair to say that Google was one of the earliest big tech companies to seriously commit to this space? Julian confirmed Google's pioneering role among the tech giants. Yeah, I think when Google got involved back in the day, he recalled, a lot of people started taking the industry a lot more seriously. They're like, oh my gosh, Google's involved. Like, this looks like a real thing. We should pay attention. He sees Google's involvement as having legitimized and accelerated the entire field. And I think we've been able to demonstrate the track record that that's been a good investment, he added, citing key scientific milestones like their Beyond Classical demonstration in 2019, showing that we can build a quantum computer that can outcompute the world's largest supercomputer or something, and their most recent breakthroughs with Willow. Given that deep research focus, how do you make sure that when those breakthroughs happen, you're ready to transition from the research and development phase to take advantage of commercialization whenever that becomes possible? How do you bridge that gap? That's a great question, Julian acknowledged. And our focus really has been keeping our eye on when do we actually get to applications that can be solved on a quantum computer better than a supercomputer. He reiterated that this head-to-head comparison with the best classical machines is central to their strategy. And so what you see in our scientific results is we're typically making that comparison, he said. And we think that the most important thing is to do that first, and then have the product side can be involved once we have like the core demonstration of the technology. It's a deliberate sequencing. Prove the fundamental capability and superiority for a specific task, then build the product around it. Speaking of those core demonstrations, why exactly was Willow such a significant breakthrough for the industry, beyond just the headlining speed comparison? Yeah, so Willow did two really important things, Julian explained, breaking it down clearly. So one, we used Willow to revisit this standard benchmark where we compare it to the world's largest supercomputer, because that's basically what our competition really is. At the end of the day, we want to beat classical computers. He described the benchmark again, running the problem on Willow in a couple of minutes versus 10 septillion years, 10 to the 25 years, way longer than the age of the universe. He emphasized the meaning. What that means is that that problem would be just impossible for a classical computer to solve. So that's one. And then, number two, he continued, highlighting the long-term significance, is basically opening the door to the future. We show that we can be what is called below threshold for quantum error correction. This technical term is crucial. What that means is Willow has shown that we can scale our system up, make very large computers in the future that will be able to solve generic and useful applications. It's the difference between demonstrating a specific, hard problem and showing a path to general purpose, fault-tolerant quantum computing. How is that different? From a technical standpoint, from some of the releases we've seen from other megacaps over the last few months. Especially for someone who doesn't necessarily understand error rates or even what 10 septillion years truly means. How can you put it in perspective? Julian stressed the importance of treating quantum computers like any other computational technology when evaluating claims. I think what's really important for people to understand who don't have as much familiarity in spaces is at the end of the day, we're making a computer. He urged people not to throw out everything they know just because it's quantum. It's a computer, and computers have specifications. They have things like how fast you can run it, how large it is, what types of benchmark problems solve. And this is how we grade ourselves. He sees this as a vital metric for tracking progress in the field. He pointed to Google's approach with Willow. So for example, with our Willow announcement, we released a spec sheet that goes with it, that tells you all the different pieces that we think are important and what the numerical values are. And you can use that to compare with other technologies to see where they're at. He also mentioned the benchmarks again. And we also run these benchmark problems, like I told you. This 10 septillion years one, that's another example where you kind of put the whole system together, see how well it runs. And you can compare it with other quantum computers. And you can compare it with the world's largest supercomputer. Is releasing a detailed spec sheet or running standardized benchmarks expected across the field after a breakthrough announcement? Did Microsoft or Amazon, for instance, provide similar details with their recent announcements? I would say that not all programs are releasing spec sheets that go with their announcements, Julian noted, highlighting a difference in how companies communicate their progress. While some information might be found in scientific papers or piecemeal announcements, Google's aim is more comprehensive. But the thing that we want to drive towards is kind of capturing all of those metrics, not just some, but all of them at the same time. To go with our announcements so people understand where the state of the art and the technology is at. This focus on transparency and providing detailed, comparable metrics is important for the scientific community and for evaluating the true state of the art. Okay, let's pivot back to the relationship between quantum computing and artificial intelligence. When we spoke previously, there was this intriguing idea that in the future, quantum computing could supercharge AI. Is that still the belief? And how might that actually work? Yeah, we think that quantum computing and AI can really complement each other, Julian confirmed. He elaborated on one way this synergy could manifest, particularly in areas like drug discovery or materials science, where understanding quantum mechanics is crucial. So there's a number of things that quantum computers can do, he began. But in this particular case, for example, AI and AlphaFold, Google's AI for protein folding. It trains on data that's provided, that's informed by quantum mechanics, but that's actually not that common. He returned to the idea of data generation. So a thing that, for example, a quantum computer could do is generate data that then AI could be trained on. In order to give it a little bit more information about how quantum mechanics works, he clarified, "Got it," meaning the quantum computer could produce complex data about molecular interactions or material properties that's impossible for classical computers to generate. And this data could then be used to train powerful AI models for related tasks, making those AI models more accurate or capable in quantum mechanical domains. You talked about having your eye on real applications within about 5 years. What are some of the potential application areas you're focused on, and how far away are we from seeing that first breakout practical use case? Yeah, good question, Julian responded. So we think we're about 5 years out from a real breakout kind of practical application that you could only solve on a quantum computer. He acknowledged the timeline debate but stood by Google's projection for this initial phase of practical utility. But there's a whole host of kind of interesting example application areas. He reiterated the core strength. Again, I mentioned that quantum computers are so interesting because there's some kind of theoretical guarantees that they can simulate quantum mechanics that's relevant in many different areas. But of course, you can pick your favorite. He then shared a compelling, tangible example often cited in the field, the story around fertilizer production. One story around fertilizer, he said. I don't know if you happen to know this one. I didn't. So it turns out that a very large amount of the world's energy usage goes towards making fertilizer using something called a Haber-Bosch process. He described the classical industrial method, and it uses like high temperature and high pressure, and this is actually like a revolution in industrial chemistry, like 100 years ago. He painted a vivid picture of the alternative before this process, because before that, the way that we used to get fertilizer, we would actually send ships out into the Pacific Ocean, chip bird poop off of these islands, out there in the middle of nowhere, and then bring them back. The Haber-Bosch process was a massive improvement, enabling modern agriculture. So this process is way better than that, Julian stated. But at the same time, If you just look in like the soil and plants, there's bacteria that will do this at like standard temperatures and pressures way more efficiently. He highlighted the tantalizing possibility. And we'd love to just copy them, right? They're doing a great job, but we don't know how. He then connected it to quantum computing's potential. But if we had a quantum computer, we could see how they work. Use that to solve, for example, this fertilizer production issue, and then save humanity a whole bunch of energy. It's a powerful example of using quantum simulation to understand natural processes and potentially develop far more efficient, sustainable industrial methods. Is that specific fertilizer application one of the solutions we could potentially see within that 5-year time frame? I think that one's a little bit further out, Julian admitted. It's a complex problem requiring a highly capable machine. But it's one of those things that, again, is like a very concrete example of how a quantum computer could be applied. What is something we might see in 5 years then? And how will we know when you've reached that benchmark? What does that measurement look like? So that's a good question, he replied, delving into the specifics of early practical applications. The first applications we think are going to be in places that are like really kind of cutting-edge physics areas where you've got some system that's sort of just out of reach of what a classical computer can do. But a quantum computer can kind of just push you past it to give you important scientific insights. This initial phase might involve simulating specific, complex molecules or materials that are just beyond the reach of current supercomputers, providing data or insights that were previously unobtainable for researchers. He also returned to the importance of rigorous validation. Something that's really important and that we take very seriously at Google is making sure that we kind of red team the problems that we're working on. Red teaming means rigorously challenging their own results and claims. Like, we want to make sure that if we're making a claim that something is better on a quantum computer, we really rigorously test it against the classical side and have people look at the best classical algorithms so that people can be confident that when we say that we have a breakthrough, we actually have it, he stressed. And that's something very important for us. This dedication to rigorous, verifiable claims is essential for building credibility in a field prone to hype. When someone like Jensen Huang, the CEO of NVIDIA, arguably the godfather of modern accelerated computing, says we're at least 15 years away from significant quantum impact, it feels like he's pouring cold water on the space. How do you reconcile Google's 5-year timeline with that much longer projection? What might he be looking at or defining differently? I would say that, there's a lot of nuance in quantum computing, Julian responded, acknowledging the differing perspectives. And it depends on kind of what you're saying, like when the revolution has happened. He suggested the difference might be in defining the scope of impact or revolution. I think there will be, early signs that, again, we're running things that can't be solved anywhere classically. And then there'll be sort of a late retrospective of like, oh, clearly quantum computing is super important. He expressed confidence in the ultimate outcome, even if the timeline is debated. And, we're confident that we're going to get there because we know that these things can do things that nothing else can do, he concluded. So I think it's just a matter of where maybe an individual would call the revolution has happened. Google's 5-year mark might be for the first demonstrably useful application, while Huang's 15+ years might be for widespread, broad-scale impact across multiple industries. It highlights that the quantum revolution isn't likely a single event, but a gradual process with distinct milestones. When do you think enterprises, beyond cutting-edge research labs, will start to adopt quantum computing? It felt like the launch of ChatGPT was that moment for AI, making it clear to businesses and consumers how they could use AI in their own operations or personal lives. When does that equivalent moment happen for quantum computing? When does it move decisively past the scientific research phase into broader consumer or enterprise use? Yeah, I think again the most important thing to look for in the next couple of years is this practical application where you can do something that has physical relevance, Julian reiterated. He emphasized the tangible link to the real world. You can kind of imagine how that transforms a real-world problem, and it can only be done on a quantum computer. He believes that demonstration will be the critical trigger. I think at that point, it behooves everyone to pay attention to the field, suggesting it becomes too significant to ignore. You mentioned that significant AI breakthroughs using quantum computers might be further away. What specific advancements or hardware milestones would we need to see to know that we're getting closer to that moment? The way that we see it is at Google, where we have something called a hardware roadmap. Julian explained, outlining their planned progression. So there's sort of a hardware track, and then there's an applications track. He described the key hardware goal, and where we want to get to on the hardware track is to build sort of a scale model of this error-corrected quantum computer. This is the future state that Willow's below-threshold demonstration pointed towards. So this is the thing that Willow opened the door to. It says this, in fact, is possible with exactly what you're building right now. You got to scale it up and make it bigger. Make it better. He described this specific hardware milestone as the true inflection point for the technology itself. We think by the time we have that machine end-to-end, we'll have completed this kind of 0 to 1 moment for making error-corrected quantum computer. We'll be you can understand it, benchmark it, look at it. This is the point where they transition from demonstrating basic error correction concepts to building a machine where error correction is an integrated, working system at a significant scale. And from the hardware side, that's really the thing that we're marching towards as fast as possible. Once they have this reliable, scaled, error-corrected machine, the challenge becomes matching it with the right problems. Then you take that machine and you match it with an application that can then fit inside that computational capacity, Julian said. And that's when you kind of have like the killer mix in quantum. It's the convergence of capable hardware and a problem that only that hardware can solve. What do you think is maybe the most unappreciated thing about the quantum computing space right now? Something the general public or even many in the tech industry might not fully grasp. Is the timeline? Julian stated without hesitation. While some like Jensen Huang project long timelines, Julian believes Google's 5-year target for a first practical application is often met with undue skepticism. To me, 5 years is not something that I hear on a regular basis. But you are very confident in that projection. He spoke about the shift in fundamental belief within the scientific community. I think, what's really interesting in the field is that like when I started a number of years ago, people actually thought that building a quantum computer was impossible. He recalled the deep theoretical challenges that made many believe it couldn't work in practice. They thought like, oh, there's no way the physics isn't going to work out. Quantum error correction is going to fall over. But that fundamental question has, for many researchers, been answered. But there's just growing more and more confidence that a quantum computer is possible to build and will be built. He highlighted the significant shift in focus. And we spend more of our time thinking about what types of things will we do with it. How is it going to work to benefit society? Rather than kind of agonizing over if the fundamental physics is going to play out. He believes the if question has largely been settled to a yes. The remaining challenge is the how and when. This underlying confidence might be what's most underappreciated by those outside the core research community. Do you think about competitors often? Who do you see as the main rivals in this race? Julian offered a perspective that broadens the definition of competition. It's a good question. I would say that truly, we think our competition here is classical computing and nature. He framed the challenge not just as beating other companies, but beating the best existing tools and understanding the fundamental limits imposed by the natural world. We want to harness nature and show that we can use quantum mechanics to actually solve problems that can't be solved in any other way. He acknowledged the difficulty of this goal. And, our competition is classical computing, which is, it's a high bar. Humanity has put a huge amount of time and effort into making computers work extremely well. He knows they need to significantly surpass that benchmark. So we need to get over that hump, but we're confident that we will. While other companies are players in the ecosystem, the ultimate victory is measured against the capabilities of classical computation. Google was arguably underappreciated in artificial intelligence for a long time, building the foundation before others seized the public spotlight. Do you think Google is being underappreciated right now in quantum computing by the general public? I will say that I think Not the average layperson doesn't understand how important quantum computing will be and the types of problems that it can solve. Julian agreed. He understands why it's difficult for people to grasp. And it can be tricky, again, because there's a lot of noise in the space. It's hard to understand from one headline or another what's really happening. He returned to the theme of tangibility and measurement. And so, again, a thing that I want to get across here is it's a physics but also an engineering discipline. You can go look at the numbers. You can really make that tangible. While he knows the underlying concepts are complex, he hopes that focusing on concrete benchmarks and specifications can help people understand the real progress being made. You're right. When you say physics and engineering, I understand that these are enormous feats, requiring incredible expertise. But it is hard for the average person to grasp onto the significance. Like we saw with ChatGPT, there was so much interesting research happening in AI. But until there was an interface you could put in front of someone, something they could play around with themselves, the average person wasn't really aware of its power. The average person is not a physicist or an engineer. What is that point for quantum computing? When do we get to that point where it feels tangible and accessible? Do we ever? Or is it going to be packaged into something else, running behind the scenes? Julian sees accessibility as a key future milestone, directly linked to the hardware roadmap. So I think, by the time we build like a scaled error correction computer, then error correction applies this interface to it. He explained that the very nature of error correction, while technically complex, makes the experience of programming and interacting with the quantum computer much simpler and more robust. That makes it much easier to access than the computers that we have right now. It makes it look much more like a normal computer and how you program it. He contrasted this with the current state. Whereas right now, if you go interface with the computers in the lab, it can feel a little bit more like a physics experiment than kind of fine-tuning knobs and things of that nature. He believes the arrival of fault-tolerant, error-corrected quantum computers will be the key to unlocking broader access and innovation. So I think when we have that sort of interface layer placed on top of it, it will open the doors to many other people being able to interact with the technology. He concluded, and I think that's going to be a very transformational moment. It's not just about the power, but making that power usable. Right now, we're at a moment in AI, especially in the last few months, where we talk a lot about this data wall. The idea that the horizontal scale of adding more data is becoming limited, and progress is now focused more on refining models or finding new architectures, because there's only so much data in the world that's easily accessible. What does quantum computing do to that chart? How does it impact models and the frontier of AI? Julian returned to the idea of quantum-generated data as a potential solution to the data wall. Yeah. Again, I think, one of the potential applications that you can think of for a quantum computer is generating new and novel data. He acknowledged the speculative nature again, but highlighted the unique potential. And there may be new methods that only kind of quantum information processing might be able to use to break down some of the fundamental barriers that may exist. But that's a little bit speculative, to be honest. Why is the promise of quantum computing generating novel data different than, say, classical AI models trying to create their own synthetic data, which hasn't always been the most effective way to push towards new frontiers? Yeah, and again, it comes back to this, Julian explained, emphasizing the fundamental difference in how the machines operate. The AI models that people use are built on classical computers, and they fundamentally can't speak the language of quantum mechanics where a quantum computer can. This is the core distinction. And it really goes down to that kind of foundational level of quantum computers speak quantum mechanics. They can access the way the universe works at the most fundamental level. This ability to directly interact with and simulate quantum systems is what gives quantum computers the potential to generate data unlike anything a classical computer could create, even with sophisticated AI. And there's a lot of potential in, solving entirely new problems by being able to build a machine that works like that. It's about generating data based on the deepest rules of reality, not just finding patterns in existing classical data. So, There you have it. From the mind-boggling speed of the Willow chip solving a problem that would take longer than the universe has existed, to the painstaking engineering required to keep qubits stable near absolute zero, to the fierce debates about timelines and the potential synergy with AI, Google's quantum computing effort is a high-stakes, complex, and potentially world-changing endeavor. They've demonstrated a significant scientific lead, backed by rigorous comparisons and detailed specifications. They believe practical, exclusive quantum applications are just 5 years away, a much shorter timeline than many others predict. They see the path to scalability through error correction and envision a future where quantum computers, perhaps integrated into hybrid classical quantum systems, tackle problems from materials science to AI data generation that are currently out of reach. But the path is fraught with challenges. The technology is incredibly difficult to build and scale. Competition is emerging, even if their current claims lack the tangible proof of Google's Willow. And crucially, Google knows from its AI experience that having the foundational technology isn't enough. The ability to translate that research into accessible, useful products is the key to winning the next platform shift. This whole journey offers us a fascinating lesson. It's easy to get swept up in hype, but it's also easy to dismiss groundbreaking potential because it seems too complex or too far off. The most impactful innovations often emerge from persistent, fundamental research that pushes the boundaries of what's currently understood or even thought possible. They face skepticism and require enormous effort to move from laboratory demonstration to real-world utility. The path is rarely straight, and the timing is almost always debated. For ourselves, what can we take away from Google's quantum bet? Perhaps it's a reminder that truly transformative change often looks impossible right up until it happens. It's a lesson in the value of long-term vision and investment in fundamental science, even when the commercial payoff is uncertain and distant. It highlights the importance of concrete proof points amidst speculative claims. And it reminds us that even for a company as dominant as Google, staying at the cutting edge requires not just inventing the future, but figuring out how to package it, explain it, and make it useful to the world. So, what do you think? Does Google's 5-year timeline for a practical quantum application feel realistic to you? Are you more excited about quantum solving scientific problems or its potential to impact AI? And how do we, as a society, ensure we're ready for the profound changes a truly powerful quantum computer could bring? Let me know your thoughts in the comments below. Thanks for joining us in this deep dive into Google's incredible progress. This is a story we'll definitely be following closely. Stay curious, stay informed, and stay healthy. And hey, if you find this exploration of the future of computing as fascinating as we do, subscribe so you don't miss our next video. We'll see you soon.